So the final question then. We've got a 1000 megawatt coal-fired power station. It burns 7.0 times 10 to the 6 kilograms of coal in one day. 2 parts per million of the mass of coal is uranium-238. The uranium remains in the residue left after the coal is burnt. The uranium nuclide 238 decays by an alpha particle emission with a half-life of 4.5 times 10 to the 9 years to an isotope of thorium. Write down the proton number Z of thorium. Well, if we've undergone an alpha decay, I might even just write the whole reaction out. So uranium-238, 92, undergoes an alpha decay, and alpha decay is 2 protons, a nucleon number of 4, so that means whatever's going to be left is our thorium. And well, if 2 of the protons are here, that means that we are left only with 90 protons for the thorium, and our nucleon number, 4 of those have gone, so that's going to be 2, 3, 4, and there are our numbers. So the proton number is 90 and the nucleon number is 2, 3, 4. Now on to part 2. Excuse me. Here we've got to calculate the mass of the uranium produced in the residue in one day. So the important part here is 2 parts per million of the mass of the coal is our uranium-238. So that will tell us 2 parts per million is 2 times 10 to the minus 6 of our total mass. So if we multiply that by the mass of the amount of coal we're burning per day, that will come out as being 14 kilograms. And on to part 3, hence show that the number of uranium atoms in the mass of uranium is 3.5 times 10 to the 25. So we know we've got 14 kilograms of uranium. So what I need to know is how many moles of uranium have we got there? Well, 1 mole is going to equal 0.238 kilograms per mole. So if I go 14 divided by my 0.238, that will tell us the number of moles. And then if I multiply that by the Avogadro's number times 10 to the 23, because there's this many atoms in a mole, that will come out at being 3.5 times 10 to the 25 atoms. And now finally on to the last part of the question. Calculate the activity of this mass of uranium. Give a suitable unit with your answer. 1 year is 3.2 times 10 to the 7 seconds. So what we know is that the decay constant, lambda, need a pen. So lambda is equal to the natural log of 2 over the half-life. Okay, so natural log of 2 is 0.693, although in the mark scheme it's just saying it's 0.69, but let's just go with what's on the mark scheme, but that's where that comes from. Half-life, which is 4.5 times 10 to the 9 years, but we want that in seconds, so 3.2 times 10 7 seconds, and that will come out as giving us our decay constant as being 4.8 times 10 to the minus 18 per second, and the activity is the decay constant, because the decay constant is the probability of a single atom decaying. If I multiply that by how many atoms we've got, that will give us the activity. So the decay constant is 4.8 times 10 to the minus 18 multiplied by the number of atoms which was given in the last part of the question, 3.5 times 10 to the 25, and that comes out giving us an activity then of 1.7 times 10 to the 8, and the activity, the unit, is the becquerel. Paper finished.